Hello. Okay, guys, can everybody hear me okay?
Yes.
Okay, just a few admits left here, and then we'll get started. Okay, first of all, the results of your midterm were pretty good. Here's the midterm, and the class average was just over 77%. Okay, so so overall, the class scored very well. And some of you took the practice exams, and that helped you. Others were pretty much up on their MyLab statistics homework, and I believe that also boded well for your performance on the midterm. Okay. Any comments about the midterm? The final exam will be run in the very same way. I'll post it to MyLab, and then you'll have at least 24 hours to finish it and turn it in. And as I did with the midterm exam, I will allow 3 submissions, and MyLab will record the best of those 3 as your grade. Okay. Now remember that when you resubmit for another test, it's going to be slightly different. Okay, did you discover that when you were taking your practice or your midterm? Okay. So, but the nature of the problem stays the same. The numbers may change slightly. Okay. Okay, so let's go. Any questions about the midterm at all? Any comments, questions? 77% was a very good grade. So I'm glad to see that those who took it performed well. And all right. Okay, so let's get started with today's agenda. So let me go to the solution set for our current worksheet here. And the current worksheet is worksheet 9. And let's see, our syllabus states that we have here 12 chapters from our textbook. And what we've been working on currently is chapters 8 and 9. Now remember, your midterm exam did not cover 8 and 9. Okay, we had been working in 8 and 9 prior to the midterm, but I did not include those as part of your midterm. All right. And to answer your non-question, but I know it's you're thinking about it now. The final exam will cover only from chapter 7, which is the confidence interval chapter, through probably chapter 11. I'll cover chapter 12 in the lecture in Zoom, but I don't think I'll put that on the final exam. So your final exam will cover chapters 7, which covers confidence intervals, through chapter 11, 7 through 11. Okay, and so the next week we'll start chapter 10, which is correlation and regression, and then we'll finish out the course with chapters 11 and 12, goodness of fit and analysis of variance. Those are two very useful topics in elementary statistics. However, as I said, I don't think we'll include chapter 12 on the final exam. I'm reserving the possibility that it might be, just in terms of how deep we go into that chapter. All right. So the final will cover chapters 7 through 11 from your textbook. Okay. Any questions about the rest of the course? Okay, here we are coming up to November, and remember we have Thanksgiving week, which is a week off. There will be no Zoom sessions that week. Now, the other part of the course are your MyLab Statistics homework. And in a couple of weeks, I'll give you another report, if not sooner, on your progress. Some of you have kept up. You're right around 50%. You have, I would say, about 6 weeks left before the end of our semester, which is officially Monday, December the 14th. So if you look in your MyLab Statistics homework assignment due dates, you'll see the December 14th date there. So you have roughly 6 weeks left to finish up your MyLab Statistics, and that's important. Okay. If you're striving to pass the course, and if you're striving to prepare yourself for the final exam, the homework assignments are key for all of that. All right. Any questions about MyLab Statistics homework? If you see yourself below the 50% range in completion, that raises a red flag. I'm not going to point fingers at anybody and bother you, but I just want to again stress the importance of getting all those assignments in and striving to get at least a passing grade, which is 70%. Okay. So you all, I've preached this a number of times, and most of you are heeding the advice, and you're getting on top of your statistics homework in MyLab. Okay. All right. If there aren't any questions, we'll press forward here with the solutions. There are 7 problems here that I want to go over with you. And these problems are from chapters 7, 8, and 9. So some of this will be review, and it'll get us caught up with our normal pace here. So this worksheet assignment will be due tomorrow midnight. So we'll go over each of these solutions in detail, so that when you write this up and submit your StatCrunch session, you'll be confident that you're doing the right things. Okay. I won't go over StatCrunch in detail with all of these solutions. We may go into StatCrunch for a bit of it, but I'm depending on you that you know the ropes in StatCrunch, and you have submitted your files, your .scs files for worksheets 7 and 8. Okay, those are still on the dock for me to give you credit for those. All right, and so let's go through these now, and you'll notice again that there's a method to writing out your solutions. Okay, so I'll be looking for various arguments, and you'll see that there's a systematic approach to each of these problems, and it's always the same approach. All right, and so please try and see the forest through the trees here, and you can see that the solutions to these problems follow a pattern, and we'll go over those solutions now. Okay. All right, so in this first paragraph here, I'm requiring you to submit your .scs file as a companion to your worksheet. Now, I did mention to you before that you can actually compose and solve all of these problems right in your spreadsheet, StatCrunch. So if you only submit to me a .scs file that shows all of your results from StatCrunch and maybe a short write-up on each of these problems that indicate that you've solved the problem completely, then you don't need to submit the Word or the PDF document. I'll see your solutions and your explanations right in the StatCrunch spreadsheet. Some of you may have had other assignments in other classes where you wrote your document, your solutions document, completely in a spreadsheet, Google Sheets, Microsoft Excel, whatever spreadsheet that you used, and you could compose your document right in the spreadsheet itself. And I'll allow you to do that here. Okay, you're all familiar now with StatCrunch. You're all familiar with its capabilities, and you can easily compose your solutions right in StatCrunch. So I'll allow that. Now, most of you will do it as you've been doing it in worksheets 7 and 8, where you submitted your word processor document along with your companion .scs. So that still works. The only thing that I won't accept is a scan. So you must submit those as two files, none of which is scanned in. Okay, so that's the only rules of the game, and that's explained here. So let's go on to the start of the first problem here. Okay, any questions about submitting your worksheets? Now remember, your worksheets are also a big part of your grade. So we'll have at least 12 worksheets when we complete the semester, and I'll count the 10 best of those 12. All right. Okay, any questions about your worksheet submissions? Okay, let's go ahead and get started here then. a sample of 16 small bags of the same brand of candies was selected. Assume that the population distribution of bag weights is normal. The weight of each bag was then recorded. The mean weight was 2 ounces with a standard deviation of 0.12 ounces. Okay. Now here's a concluding statement that's important. The population standard deviation is known to be 0.1 ounce. So we're given the population standard deviation, and refreshing our memory about how these tests are chosen, basically you can choose the z-test or the t-test for the test of the mean or the means. Okay, in this case we have a single mean. And even though the sample size plays a role in deciding whether it's t or z, the trump card is that the standard deviation is known, which puts you into a z-test regime. So right away you're saying, we're given the population standard deviation, so therefore I can safely use a z distribution even though the sample size is less than 30. Okay, so in the first question here, which distribution should you use? Well, it's, as I have explained, it's the z. And the reason is the standard deviation is known. Okay. And the problem is to construct a 90% confidence interval for the population mean weight of the candies. And here in this next box, I give you the StatCrunch output. Okay. So the results box here gives you all of the information you need for the construction of the interval. It gives you not only the standard error, but it gives you the right limit and the left limit, okay? The lower limit and the upper limit. And so here's our results, okay? And what is the error bound? Okay, remember the error bound is half the width of the confidence interval. And the way that we calculate the error bound, your textbook gives you the formula for that in chapter 7. All right, and the formula is the critical value z, which depends on the confidence level of the interval you're constructing. In this case, we're constructing a 90% confidence interval, so that means that alpha over 2, alpha here is 10%, and alpha over 2 is 5%, okay? So the critical value is based on the confidence level, and the confidence level here is half of alpha, which is 0.05, times the standard error. Now the standard error, remember, is sigma over the square root of n. And that turns out to be 0.025 for the given n, which is 16, and the given standard deviation for the population, which is 0.1. So this fact here, that the sample standard deviation was 0.12, that's not relevant now because we actually were given the population standard deviation, as I said, which trumps that, and therefore we can use a z distribution. And remember, this critical value is based on the z distribution, putting 5% probability in the right tail, okay? And that turns out to be 1.645. All right. So if we check that using our normal calculator here, and so if I want the right tail, I'll use the greater than or equal to, and I'll specify that the right tail has 0.05 probability, and then you get your critical value here. Okay. And most of you have done this in StatCrunch. Okay. So now we can go ahead and multiply our standard error here times z of 0.05, which we just saw to be rounded to 3 decimal places. It's 1.645. And here's our standard error times the critical value gives us our error bound for the mean, the EBM. And that turns out to be 0.041, rounded to 3 places. Okay. Now, if we want to do this for 98%, then our confidence level, alpha here, is 0.02. We have that to get 0.01. And then we go back into StatCrunch. And to calculate the EBM, we multiply this value z.01, which is now the critical value. Standard error remains the same, doesn't it? Okay. And we get an error bound of 0.058. So we see that if you increase the confidence level, you get a wider interval. Okay. All right, let's go back to StatCrunch for a moment and calculate our new critical value here based on 98% confidence. So we change 0.05 to 0.01, and we get the 2.33, right? Okay, any questions about this problem here? Okay. And in the final question, explain why the CI, okay, all right. And here you construct the 98% confidence interval, and you see that you get a larger interval here. So a higher level of confidence does require a larger CV, right? And that gives you a larger interval. So to be more confident in your estimate, you can increase the confidence level. Okay. All right. Any questions about number 2? Okay. All right, let's go to the next problem here. Public Policy Polling recently conducted a survey asking adults across the US about music preferences. When asked, 80 of the 571 participants admitted that they have illegally downloaded music, right? Now, this poll, I think, is dated, let's see, a few years ago, there was a site that allowed you to download music free of charge. And right now, the name escapes my memory. It's been a few years now. They cleaned that up, and now, yes, go ahead.
Oh, I was asking, were you talking about LimeWire?
No, I haven't heard of that one. Gosh, the name of the program is on the tip of my tongue because everybody was using it to download their music. Okay. But now what do we use? We use the iTunes, we use Spotify, Amazon Prime, and so on. We're all paying for our music now, which is actually not a bad deal, is it? I mean, they don't charge too much for those programs. Okay, all right, so here's the situation here. We have a problem here, okay. The survey was conducted, yes, here's the date of the survey, May of 2013. Okay, all right. List some factors that could affect the survey's outcome that are not covered by the margin of error. Okay, now remember in a poll, we're told what the margin of error is. So, you know, that actual population proportion could be up to plus and minus 4 points difference. All right, but there might be some other factors that come into play here. All right. We're using a phone survey, and once the surveyed users are selected from however the researcher selects them, now she has to contact them by phone, okay? And she has the resources to call a number of respondents, but if they're not available, and many of our phones are set up that if an incoming call comes in with an unknown caller ID that's typically listed in your contacts, the phone may not even ring. Some of us have our phone set up that way, all right? Thinking that it might be a spam caller, telemarketer caller, whatever it is, and we don't even answer the phone if it's not a number listed in our contact list. So there may be problems in actually getting a large enough sample just due to people not responding from a phone call. Now, this is a sensitive question, isn't it? If someone calls you and asks you if you're doing something illegally, you're likely to hang up, right? You won't even answer, especially if you're guilty as charged. All right. So others, yeah, I download music illegally. What's the big deal? If I can do it technically with the technical things that are out there, I'm going to do it. All right. Okay, and they'll offer and volunteer that information. Okay, so there are some you know, drawbacks, not just to the airbound for the proportion, okay, and therefore there might be some problems in the sampling itself. Okay, we won't go into those in any detail, but this problem just again outlines some of the pitfalls in sampling, okay, especially by phone, all right? And then the last question says, without performing any calculations, describe how the confidence interval will change if the confidence level changed from 99% to 90%, okay? And as we know, when the level decreases, the error bound decreases, and the 90% confidence interval will be narrower, right? It'll always be narrower, okay? All right, any questions about the number 2 here? And notice it's not a mean, it's a proportion. In a sense, it is a mean when we know that the binomial distribution is the model for developing the confidence interval. Okay, we approximate the binomial distribution using the z-distribution, right? Okay, number 4 here says, the mean number of sick days an employee takes per year is believed to be about 10. Okay, some of you have health and welfare benefits associated with your employment, and most employers will allow sick leave. Now, the employer has to choose how many days of sick leave is going to be offered as a benefit. So the members of a personnel department believe that it's not 10, okay? So they take a survey of 8 employees. Now, we're not told in this problem whether they believe it's more or less than 10 days. They're just casting some doubt on whether the number is 10. Okay. So the number of sick days that the 8 sampled employees took for the past year are given here in this list. 12 days, 4 days, 15 days, and so on. Our random variable is the number of sick days they took for the past year. And the question is, should the personnel team believe that the mean number is 10? Okay. So let's go through our list and write out the solution to the problem. Okay, so pay attention to, and you've already gone through this list, okay? So in order to get full credit for your solution, at a minimum, you should list these several steps. And I think I've packaged them into about 6 steps here, and we'll go through these step by step. Remember, in worksheets 7 and 8, you've already done something very similar to this. Okay. All right, so first things first, let's state the claim to be tested. That'll go at the front piece of our argument here. And that'll serve to focus us into the problem that's required here, into the solution. Okay. So here's our claim. Members of a personnel team do not believe the number of sick days an employee takes per year is 10. And we convert that into a set of 2 hypotheses, the null and the alternative hypothesis based on the claim. Now remember, the claim could be not equal to 10 days or less than or greater than 10 days. Those are the 3 alternatives that we have here. Now, the claim that it's equal to 10 goes into the null hypothesis. Okay, so we claim that in the null hypothesis we'll set mu equal to 10. The evidence or the sample either supports that claim or it doesn't. All right. And the alternative is that mu is different than 10. Okay, and we got that straight out of the wording of the problem. Okay, now up here, we're not given the significance level of the test. We're told only that we have a sample of 8 values here, and we're given the statement of the claim, so far so good. So we'll choose alpha, our significance level, to be 0.05, all right? And then let's state what the test statistic is now. And this falls under the T regime, doesn't it? T because we're not given the population standard deviations. And since we're not given the standard deviations for the population, the only thing that can save us from a T is a high sample size, and it's not greater than 30. In fact, it's only 8. So not given population standard deviations, and we're using a small sample size. After all, the company may only have 30, 50 employees. It may be a small employee population, and therefore our sample size might be small, as it is in this case. Okay, so we've determined that the T is the right fit for this problem. Okay, now the critical value for this so-called two-sided test, right? Since this is not equal to, the critical regions will be either too small or too large. Okay, so if we decide that the statistics that were given, the sample mean, the sample standard deviation, we're not given those latter two statistics, are we? We're only given the raw data in this problem. So we'll have to calculate those statistics and then use those statistics in our test. Okay. All right. And we can determine the critical value for the test. And when we take the t-score using those sample statistics, we can determine where that t-score falls. Does it fall in the critical regions or not? Does it fall into the intermediate range, which would lead us not to reject? So let's calculate our t critical value here with n-1 degrees of freedom, and we come out with these two critical values, each leaving alpha over 2 area in the tails. So each of those tails leaves 0.025 area. Okay. And again, if we go to the calculator in StatCrunch, we can pull out those two critical values. So let's go to our calculators, come down to the t-distribution here. All right. And then we'll cook up a two-sided critical region here. So we'll use the between option up here. Our degrees of freedom, as I said, is 7, since the sample size is 8. And we want 0.025 area. Sorry, we would like 0.95 area in between the two critical values, right? Which is saying, the same thing would be saying that we leave 0.025 area in each of the two tails. So let's just do it this way. We'll leave 0.05 area in the two tails combined. Uh, 0.95, I keep doing this. Okay. All right. And there we get the two critical values. Okay. 0.95 area in the so-called non-rejection region, right? The region between the two critical values here for this two-sided test. Okay. And t-distribution with 7 degrees of freedom, leaving 0.95 area in the non-rejection. Sometimes the text calls it the acceptance region. We won't reject, we'll accept the null. Okay, and those two values are symmetric values, negative and plus 2.365 if we round to the 2 decimal places, 3 decimal places, excuse me. Okay, so here are our two critical values, and now we can calculate a t-score, which is x bar minus mu divided by the standard error. StatCrunch does that for us, okay, and gives us the table of results here, okay? So StatCrunch, when you do the t-test for a single mean with 7 degrees of freedom, will return these statistics for you. And once we compare the t-score, and you can see that down here in the second box, the t-score is about 1.12, rounded to 2 decimal places. And as we see, that's between the two critical values. That is, it falls in the non-rejection region, so we would not reject. And the other clue here is the p-value for the t-score, right? It's fairly high. It's almost 0.3, certainly greater than the significance level. So if the p-value is high, the null hypothesis will fly. So we have two ways of looking at this. We compare our t-score based on the sample mean and the sample standard deviation with the critical region, which in turn was determined by the significance level, or we can just take a peek at the probability value and see that that's high, certainly higher than 5%. So that would lead us to not reject. Okay, and that's given to you here in step 5. And then in the last step, you must state your conclusion in words, because remember, when you're doing research, you're sharing these results with lay people who are not familiar with statistical procedures necessarily. And you would state something like this: there is insufficient evidence to conclude that the mean number of sick days an employee takes per year is different than 10. We don't reject the null hypothesis. Okay. Now we can go back and take a look at the sample mean, and the sample mean is a little over 8 days, which would indicate that it's less than 10. Okay, but we're not concluding that. We're just concluding that, in fact, it's probably not different than 10. Okay? At this sample size, at this significance level, at this standard deviation, at this standard error, the evidence, the sample is not sufficient to conclude that it is different than 10. Okay? Any questions about this test of one being, number 4? And I want you to please pay attention to how I've written out the solution here. I've organized it into these 6 steps. First step, state your claim. Second step, state that in terms of the standard statistical notation for hypotheses, H0 and H1. Specify your significance level. Typically, it's given to you. And I would say that in most cases, it's one of the standard significance level, 1%, 5%, 10%. Okay? But it can be any alpha, right? And then state the critical values based on alpha. Do your results in StatCrunch to give you the t-score and the p-value for the test statistic, okay? And then once you have those under your belt, then you can compare your t-score, your t-statistic with your critical values to see whether it falls in the rejection region or not. And if it does, you reject in favor of the alternative. And if it doesn't, you cannot reject the null hypothesis. Okay. And then the other important thing here is the bottom line. Taking all this work that you've done and writing out a final statement based on your analysis. The data do not provide sufficient evidence, or simply there is insufficient evidence to conclude that the mean number of sick days is different than 10. Okay, does this make sense? And you've already dipped your toe in the water, right? You've already done 7 and 8, which already familiarized you with this procedure. Okay. And those of you who elect to do this in your StatCrunch spreadsheet and only submit a .scs file, what I'll be looking for in the body of your spreadsheet is this outline, touching all the bases from 1 to 6. Okay? And I'll be looking at your organization of how you actually state your solution, touching bases with all of these points here. All right. Okay. Any questions about number 4? Are we good there? Okay. And let's go to the next one here. A poll done for Newsweek found that 13% of Americans have seen or sensed the presence of an angel. A contingent doubt that the percent is really that high. It conducts its own survey. Out of 76 Americans surveyed, only 2 out of the 76 had seen or sensed the presence of an angel. As a result of the contingent's survey, would you agree with the Newsweek poll? All right. So we're going to test a proportion. That'll put us in the Z regime. Okay. And we scanned the problem here to see what we've got. We've got a purported population proportion here of 13%. And we have a survey, a sample. 2 out of 76 Americans have seen or sensed a presence of an angel. Okay, so let's see where the statistics there lead us. Okay, would you agree with the Newsweek poll? Okay, so we're in the two-tailed regime, aren't we? Because we're not saying that it's less or that it's more. Would you agree? Oh wait, I'm mistaken here. Let me backtrack. The contingent believes that the percent is not really that high. They believe it's less. Sorry, I skipped over that part. Okay, I got ahead of myself. Okay, so this is the key claim right here, right? The contingent that collected the sample doesn't believe that it's that high. They believe that it's less. Okay, so here's our claim then, right? The percentage P of Americans who have seen or sensed the presence of an angel is believed to be less than 13%. Okay. They have doubt that it's that high, so they believe it's less. Okay, so here's our null, that it's equal to 13% against the alternative that it's less. Okay, is that clear? And that's all based on the wording in the problem. Okay, all right. All right, now we know that the test for the single proportion is always a z distribution, all right? And we can go up to our statistical calculator in StatCrunch to calculate a left tail critical value, which leaves 0.05 area in the left tail. Again, we have chosen our significance level to be 5%. It wasn't given to us, so we chose it, we let it be 5%, okay? And then again, we can go into StatCrunch here to calculate our critical value. Let's go to the normal calculator. Okay. And we'll set up a left tail, and the left tail will have 0.05 area in it. Because we've chosen alpha to be 0.05 for this this left tail test. And there we get our critical value there of negative 1.645, okay? We've rounded that to 3 places. Okay, now we're good to go. We can go into StatCrunch, calculate our test results using the one sample test of the proportion here, okay? And we get a z-score pretty high here on the z-scale, right? Okay. This is a little awkward here because there's a minus sign here. Okay. Remember, the z-score is based on p-hat, which is 2. Remember, p-hat here is 2 divided by 76. That's the sample proportion. In the contingents survey, they found that 2 out of the 76 sampled sensed the presence of an angel. Okay? So our sample statistic, p-hat, is 2 over 76. That turns out to be about 0.0263. And if we normalize that by subtracting the hypothesized mean of 13% and dividing by the standard error, we get a fairly high z-stat. Okay, not quite 3, 2.69 if we round to 2 places. And then the companion p-value for that test score, which is fairly high, is fairly low, 0.0036. Okay. Another way to conclude this is compare your z-value here, your z-score of negative 2.688 with your critical value, seeing that it falls to the left of that value, falls in the rejection region. So we will reject the null hypothesis. Okay. If the p-value is low, the null hypothesis is a no-go, right? Too low, doesn't exceed alpha, so we cannot accept, we have to reject based on this evidence. Okay. So the evidence support, or there is enough evidence to conclude that the percentage P of Americans who have seen or sensed the presence of an angel is less than 10%. Okay, so the contingent has some evidence here to believe that it's actually less than 13%. Okay, any questions about the test for a single proportion? And again, I have broken this down systematically into these 6 steps or so. Okay, just to kind of do the bookkeeping, keep track of what we're doing, and you'll see this pattern over and over again in hypothesis testing, broken up into these various steps. Okay. Okay, let's go to the next problem here. If I can get my scrolling to work here. Okay. All right. The mean number of English courses taken in a 2-year time period. Okay, let me zoom up a little bit here. Okay. The number of English courses taken in a 2-year time period by male and female college students is believed to be about the same. An experiment is conducted and data are collected from 29 males and 16 females. The males took an average of 3 English courses with a standard deviation of 0.8. The females took an average of 4 English courses with a standard deviation of 1.0. Are the means statistically the same? So the claim is that the means across gender are the same. Okay. And so we'll set up all our mean, our null hypothesis and our alternative hypothesis based on that claim. So we'll do that in symbols. Now, in the past, I have gotten solutions that simply write out in words what the null is. The null would be the mean number of English courses taken by male and female students is the same. Well, what we're looking for here in this first step is both a wording of the claim and then a transliteration, if you will, into mathematics using common symbols for the null and the alternative here. So the null, correctly stated in statistics, would be H naught, the difference in means in the population means is 0. Okay? Against the alternative that it's different than 0. That is that the population mean number of English courses taken by males and females is different. Okay? So you must embody your claim in terms of these statistical symbols. Okay? And again, the significance level for the test is not given here, is it? Okay, so we'll take 4%, not 5. Why 4? Well, just to change it up a little bit. Okay, so we'll specify the significance level to be 0.04. All right, and now we have a 2-sample test here. So the number of degrees of freedom is going to be n1 plus n2 minus 2. This is a 2-sided test, right? So we have to divide 0.04 in half to get 0.02, and then read out from your statistical T calculator the 2 symmetric T critical values here based on alpha over 2, 0.04 over 2 is 0.02, and n1 plus n minus n1 plus n2 minus 2, which is 29 plus 16 minus 2 would give us the 43, and then read that out from your T calculator as plus and minus 2.118. Okay. Now go into your 2-sample t-test for the mean and calculate your test based on your sample statistics. And we're given all of the sample statistics up here for the males. We had a sample size of 29 with a standard deviation of 0.8, and the females a standard deviation of 1.0 based on a sample size of 16. Okay, so with that summary, we can go into our test, and our t-stat is really large here. Our normalized t-score, which is the difference in sample means minus the difference in population means in the numerator. The difference in population means in the numerator is simply 0, right? Okay, so we take the difference of the sample means across the two genders and divide by the standard error. Okay, and we get a t-stat of 3.67 if we round to 3 places. Okay, and that's going to be outside the rejection region here, right? Okay, it's going to be way out in the left tail there, which puts us in the rejection region. And we can state now, or we can look at the p-value, right? The p-value is really small. Okay, tenths, hundredths, thousandths, 10,000. So it's 7 10,000ths according to our calculation there. Really, really small. So we reject the null and we say that there is sufficient evidence to conclude that the mean number of English courses taken in a 2-year time period by male and female college students is different. Okay. All right. Okay, any questions about this 2-sample t-test for the mean? And again, I've listed the solution by procedure here, breaking it up into these 6 steps. Okay. All right. Step 1, going from the claim and the hypotheses right down to our conclusion, concluding that there is sufficient evidence based on the sample, et cetera, et cetera. Okay? All right. Are there any questions? Let me check your chats here. Napster. Yes, that was the one. How many years ago was that? Does anybody remember? 10 years ago? A little while ago, right? Okay, Napster. All right. Okay, I think we're in number 7 now. Okay. Okay, how many people have non-hybrid sedan cars anymore? I'm guilty. I have to raise my hand. I don't have a hybrid car. Yeah, I guess I wish I had one, but I don't. Anyway, so some of you do have hybrid cars out there, right? And some of you have electric cars, which is even better. So anyway, the claim by the manufacturers is that non-hybrid sedan cars have a lower mean miles per gallon, let's abbreviate that MPG, than hybrid ones. Okay, that non-hybrid sedan cars have a lower mean miles per gallon than hybrid ones. Okay, all right. Non-hybrids. Okay, that's a pretty It's a pretty bold claim, isn't it? So here's the data. Consumers test 21 hybrids and get a mean of 31 miles per gallon with a standard deviation of 7 mpg. And then in the sample of the non-hybrid sedans, whose sample size is 31, the mean MPG was 22 with a standard deviation of 4. Okay, looks like a significant difference there, right? All right, so here's the claim to be tested. Non-hybrid sedan cars have a lower mean MPG than the hybrid ones. Okay, so let's set that up. Now remember, mu1 is going to represent the population mean for the non-hybrids. All right. So in the alternative hypothesis, where the claim embodies the alternative that the difference in MPG for non-hybrids and hybrids is less than 0. That embodies the statement in the claim that the non-hybrids actually have a lower mean MPG than hybrids. Okay. Let's see, is 0.5, is the significance level stated here? No, it's not given to us. So we can set it up to be 0.05. What is the test statistic? Okay. The test statistic here is going to be here a z, because, and I didn't read this part here when we were going through the problem, the population standard deviations are known to be 6 and 3 respectively, okay, for non-hybrids and hybrids, okay. Even though the sample sizes are small, we get a pass on the t, we can use the z, because the standard deviations are known for both populations, and they're given here to be 6 and 3, okay? So we use the z distribution since the population standard deviations are known. Check that box, and now go into your z calculator. We did this earlier, and for this left tail test, mu1 minus mu2 is less than 0. Our critical value is in the negative tail, and it's negative 1.645. Calculate our z-stat, and as we surmised earlier, it would be fairly large, okay? Because remember that the means were quite a bit different. And in terms of standard deviations, the normalized z-score is way, way out. And here's the negative sign here, don't forget that. So we're way out in the left tail, negative 6.36. And correspondingly, the p-value is fairly small, okay? So for those reasons, we're going to reject the null, either because the p-value is so low, and correspondingly, the t-score is way, way out in the left tail, okay? We're going to reject the null. And so the researchers have sufficient evidence to conclude that the non-hybrid sedan scores have a lower mean MPG than hybrid ones. No surprise there. All right. Now, one other fact that I'll share with you is that my non-hybrid sedan is a diesel car. And those are supposedly supposed to be cleaner than gasoline, but there's some controversy about that as well. All right. In the last problem here, let's see, it states that researchers conducted a study to find out if there is a difference in the use of e-readers by different age groups. Okay. Randomly selected participants were divided into 2 age groups. In the 16 to 29-year-old group, 7% of the 628 surveyed use e-readers. E-readers, Kindle, gosh, I can't even think of the others out there. All right, there are a number of e-readers, right? While 11% of the 2,309 participants 30 years old and older use e-readers. Okay? All right, so the older age group here use 11%, the younger age group use 7%. Okay. And up here, we're conducting a study to find out if there is a difference. Not if they're different. That is, not if one age group uses it more or less. All right. So we're only claiming that there is a difference. That'll lead us to a two-tailed alternative here. So our claim is that there is a difference in the proportion of e-readers by the 2 different age groups. So we'll translate that into this set of 2 competing hypotheses. H naught is there is no difference against the alternative that there is a difference. Okay, so we get the two-tailed alternative here for the 2 proportions. And again, there's no given stated significance level here. So we're going to go with 5% significance level. Okay. We use a Z distribution because it's a proportions test between 2 samples. And at the 5% significance level, we get the 2 symmetric plus and minus critical values of plus and minus 1.96. So the 2 tails, left and right, each have half of 5% probability in the tails, which is plus and minus 1.96. Okay. Now we do the our 2 sample proportions test, and we come up with the following sample statistics here. Okay, and we get we can convert these percentages up here in terms of 2 values. So we'll take 7% of 628, and that sample proportion would be, no, I guess we're not given the sample proportion. We're given the counts. So 13% of the sample size there here, 7% of 628 for the younger age group. And if we take 7% of 628, we'll get 43.96. This is just the way that StatCrunch is displaying this. And similarly, for the other age group, we see that 11% of 2,309 is about 254, right? Okay. Now we can calculate the difference in the sample proportions, right? That's easily done. We just take the difference between, and we're using the first population as the population proportion of e-readers in the age group 16 to 29. So that's P1. P1 hat is 7%, P2 hat is 11%. The difference is minus 4%, okay? And if we normalize that using the standard error, we get our z-score here. And the z-score is fairly high, almost 3, -3 that is. And you see a very small p-value, okay, less than 1%, okay? So that'll lead us to reject the null, either by comparing our t-score, or z-stat, excuse me, of about 3 with our critical values of plus and minus 1.96. So -3 is going to be much smaller than -2. So that'll lead us to reject. And we see that the calculated p-value from StatCrunch is less than 1%, certainly less than 5%, so that's too small. And our conclusion is there is sufficient evidence to conclude that there is a difference in the proportion of e-readers by the two different age groups. Okay? Any questions about any of these problems? Okay, I have a question in the chat list here. For problem 6, can you go back to question 3? So let's go back to, see. Okay. Okay, so let's go back to problem 6 here. Okay, we have the two-sample test of the mean here. And we're going to use a t-statistic. The sample standard deviations are not known. Okay. All right, and so we're at step 3 here. And could you verbalize the question for part 3?
Yeah, so I just had a question about, like, how did you know it was a t distribution and not like anything else?
Well, the first clue is that the standard deviations for the population are not given to you.
Okay.
Now, the sample sizes are marginally small. So that would typically throw us into a T. And furthermore, the standard deviations are not given. The population standard deviations are not given. Okay. Yeah. So that would conclude. Now, also, StatCrunch gives you two choices: pooling the variances or not. And typically, unless we're told that the standard deviations for the populations are different, we should pool the variances. So there's an option in StatCrunch to pool. Okay, so we would choose that option unless we're told that we can't assume so. Okay,
Yes, thank you.
all right. And then I have another question here, uploading the recording. Yes, I'll upload the recording. I'll try and get that to you. Typically, I like to give these to you after you hand them in. Okay, but let me try and get it up and posted before tomorrow, so that you have time to look at it before you turn it in. Is that fair? Okay, guys, I have office hours starting at 11:30, so let me end the meeting now, and then in 10 minutes or so, I'll come back online, okay? So I'll see you then. Bye now.
Okay, bye. Thank you.
Bye-bye.